December 1st, 1965. Retrospective. Former engineers from Tachikawa visited American plants, observing assembly lines, automated presses, and standardized parts. They recognized a familiar philosophy, the same principles that had once amazed them in 1943, now enhanced and refined. These visits underscored the irony. The captives of war had become teachers for the victors of peace. As this story demonstrates, the Boeing B-17 Flying Fortress dropped thousands of tons of bombs, flew countless missions, and became a symbol of American wartime ingenuity. But its most enduring legacy was not combat. It was industrial education. Japanese engineers learned that precision, standardization, and scalable production, not individual craftsmanship, determined the outcome of industrial competition. The captured B-17s were gone, yet their lessons shaped generations of engineers and manufacturers worldwide. History isn't just about what happened. It's about what we learn. Take a moment today to study the systems around you, the processes you rely on, and the efficiency of your own work. Just like Japanese engineers transformed their industry by learning from a captured B-17, you too can transform your world by observing, analyzing, and applying the principles hidden in everyday challenges. Tens of thousands of rivets were measured. Diameter variation was less than 0.0002 inches. Installation depth variation under 0.0001 inches. Such precision, achieved consistently across hundreds of rivets, was impossible by hand. Proof of the industrial philosophy that made the B-17 unstoppable in quantity. By mid-1944, it became evident that Japan could never match this combination of design, production, and maintenance philosophy. Turbo superchargers, high-altitude engine performance, and other advanced systems examined from the B-17 were understood conceptually by Japanese engineers. But producing them consistently was beyond wartime industrial capacity. Skilled artisans could not compensate for systemic deficiencies in standardization, interchangeability, and mass production. August 15th, 1945. Japan surrenders. The war ended, and the captured B-17s were either destroyed in air raids or dismantled. Yet the lessons they imparted endured. Engineers who had measured rivets, engines, and hydraulic systems carried this knowledge into post-war industry. They understood that matching American industrial capability required more than copying designs. It required implementing production systems. By the mid-1960s, Japan had transformed. Factories that once relied on skilled craftsmen embraced automation, precision tooling, and systematic assembly, producing automobiles, electronics, and aircraft with unparalleled quality. Toyota's just-in-time manufacturing, Sony's precision electronics, and Honda's scalable engine production reflected lessons first glimpsed on Tachikawa Airfield. The B-17s had taught Japanese engineers that industrial success depended not on superior materials or designs alone, but on the organization and philosophy of production itself. While Japanese planes were marvels of craftsmanship, the B-17 embodied repeatable precision at scale, enabling rapid production, efficient maintenance, and operational redundancy. Lieutenant Shiyama remarked, "The enemy does not rely on individual skill for their success. Their system makes skill optional." February 3rd, 1944. System synthesis. Engineers compiled all data into comprehensive reports, detailing tolerances, materials, rivet depths, electrical schematics, and hydraulic pressures. One striking observation was the degree of standardization across aircraft. Components from different bombers fit perfectly, a principle Japanese manufacturing could not replicate at the time. This insight resonated deeply. It was not merely a lesson about the B-17, but a revelation about the limits of Japan's wartime industrial capacity. Field tests continued through spring. Major Uno and Captain Yagi conducted mock combat flights with Ki-44 Tojo fighters, recording defensive gun performance, handling under full bomb loads, and structural response to simulated battle damage. Every engagement highlighted a chilling truth. Even if Japan could produce more skilled pilots, the sheer industrial output of American factories ensured the B-17s would outnumber and outlast any opposition. April 10, 1944, brought the final structural evaluation. Engineers intentionally stressed damaged components from previous ground accidents to understand material limits. Wing spars, fuselage panels, and rivets displayed precision that suggested automated or semi-automated manufacturing techniques, rather than individual artisan craftsmanship. Toru Saito documented these findings in Asahi Press, emphasizing that the captured bombers were a lesson in industrial warfare, not just military engineering. Japanese readers, from factory engineers to military strategists, began to grasp that America's advantage was deeply systemic, built into the very bones of its machines. As Part 5 closed, Major Saito prepared a briefing for higher command. He emphasized the unavoidable reality. Even Japan's best pilots and engineers could not match the operational output of American industry. The B-17, once merely an aircraft, had become a symbol of industrial inevitability, a teacher showing Japan the limits of its own production methods. In Part 6, we will reveal how these lessons shaped Japanese post-war industrial transformation, the final fates of the captured B-17s, and the ultimate acknowledgement by Japanese engineers that they had never achieved automation at this level, concluding with a final call to action that ties history to lessons for modern viewers. January 12, 1944. Tachikawa Airfield, Tokyo. The harsh winter air did little to cool the intensity of the examinations underway. By now, Major Kazuyuki Saito and his team had been studying the captured B-17Es for nearly 2 years. The bombers, once symbols of American military might in the Pacific, had transformed into living textbooks on industrial engineering, mass production, and systematic design. Engineers had already documented engines, hydraulics, electrical systems, armament, airframe structures, and field maintenance techniques. But now attention shifted to post-war implications and industrial philosophy. The Japanese engineers began cross-referencing their findings with other captured aircraft, including Nakajima Ki, 43 Oscar fighters, and Mitsubishi G-4M Betty bombers. They noted stark differences. The cockpit ergonomics were also dissected in detail. Test pilots Major Uno and Captain Yagi guided engineers through repeated flight simulations, evaluating control layouts, instrumentation, and emergency procedures. The B-17's design philosophy emphasized efficiency, simplicity, and redundancy, allowing crews to operate effectively under stress. Japanese pilots noted that while Japanese bombers often required multiple specialists to manage systems, the B-17 could be flown and maintained with fewer, less specialized personnel, a stark advantage in sustained operations. In addition to structural and system analysis, the engineers studied field maintenance and component replacement procedures. Every subsystem, from the bomb racks to the oxygen system, was designed for rapid servicing. Replacement parts could be installed with minimal training and tools. Saito documented these observations meticulously, understanding that the underlying philosophy, precision manufacturing enabling scalability and operational continuity, was the true genius of the aircraft. By late October 1943, Japanese engineers had reached a sobering conclusion. The B-17 was not superior solely because of its aerodynamics or engine power. Its advantage lay in industrial philosophy, mass production, and systemic design. Every component, every subsystem, every structural element had been created to ensure reliability, maintainability, and rapid scalability. Japan's reliance on skilled craftsmanship could never compete with a system where automation and precision tooling replaced the bottleneck of artisan labor. October 7, 1943. Tachikawa Airfield, Tokyo. Autumn winds swept across the sprawling runway, carrying with them the faint hum of distant aircraft and the disciplined footsteps of engineers moving between the captured B-17Es. By now, Major Kazuyuki Saito and his team had spent months meticulously documenting the bomber's systems, and the focus had shifted to its structural integrity, wing design, and landing gear mechanisms, the elements that allowed the aircraft to endure punishing operational conditions while remaining remarkably reliable. The engineers began with the wings, dissecting every spar, rib, and panel. Each main wing spar had been machined on automated equipment, drilled to precise patterns that matched perfectly across all captured aircraft. Wing ribs, stamped from master dies, allowed control surfaces to be interchangeable. Ailerons, elevators, and rudders fitted seamlessly without adjustment. The precision was unprecedented. Lieutenant Sciamma recorded measurements down to fractions of a millimeter, noting that such uniformity was impossible using traditional Japanese handcrafting methods. Landing gear assembly provided another eye-opening revelation. Main struts were forged, heat-treated, and machined with automated lathes, while actuating mechanisms relied on hardened, standardized components. Every unit could be replaced quickly in the field without specialized tools. Saito observed, "Our engineers require years of training to achieve what these machines accomplish automatically." In Japanese production, the landing gear of a single aircraft could vary slightly from another, requiring field modifications, a slow, labor-intensive process. The engineers also observed the psychological impact. Junior officers, witnessing the precision and durability of these captured bombers, were astounded. They realized that American industrial capacity could replace lost bombers faster than Japan could build interceptors, creating a profound strategic advantage. The lessons extended beyond individual aircraft. They highlighted systemic differences in industrial organization. Throughout September, Major Saito compiled the findings into detailed reports. Photographs documented every component, from engine pistons to rudder control cables. Toro Saito of Asahi Press recorded these examinations for publication, noting the profound gap in production philosophy. The American approach is systematic, modular, and scalable. It is a war machine not only in combat, but in its very manufacture. By the end of Part 4, Japanese engineers fully understood the B-17's strategic significance. Its superiority lay not merely in performance, but in the ability to maintain operational readiness, mass-produce components, and minimize reliance on skilled labor. For every Japanese plane downed, the Americans could field replacements with consistent quality and speed, a sobering realization that foreshadowed the challenges Japan would face in prolonged conflict. And yet, the story was far from complete. In Part 5, we will explore how the engineers analyzed the bomber's structural integrity, wing design, and landing gear, uncovering innovations in mass production techniques and automated assembly that Japan could not hope to match. These discoveries would cement the B-17's role not just as a machine of war, but as a lesson in industrial superiority. Japanese aircraft, often more complex in layout, relied on pilot experience and training to manage the systems. The ergonomic design of the B-17 cockpit was a revelation, demonstrating how American designers valued human factors alongside mechanical ingenuity. The oxygen system was also scrutinized. Engineers noted precision regulators controlling flow to each crew position, bearing stamps from manufacturers unfamiliar with aviation, automobile parts companies producing aircraft-grade components. This illustrated not only American innovation, but also the industrial depth and adaptability of U.S. manufacturing. If automobile companies could supply precision parts for aircraft, the scale of production could be multiplied rapidly. Japanese industry, limited by specialized labor and less standardized tooling, could not replicate this adaptability. Hydraulic and electrical systems were further analyzed. Engineers disassembled actuators, valves, and switches, documenting standardized connections and modular designs. Wiring employed machine-crimped terminals, consistent wire gauges, and simple replacement procedures. Japanese aircraft required soldering and adjustments for even minor repairs, which significantly slowed field maintenance. The realization was stark. The B-17's design philosophy prioritized rapid deployment, easy maintenance, and operational continuity, all enabled by industrial standardization. Test flights during September 1943 reinforced these findings. Japanese pilots, practicing mock interceptions with Ki-43s and Ki-44s, experienced firsthand the bomber's defensive capabilities. Even coordinated attacks often failed against overlapping fields of fire. The engineers noted that the B-17's effectiveness was amplified not just by design, but by production philosophy. Every aircraft built to exacting standards, interchangeable parts simplifying repairs, and maintenance requiring minimal specialized labor. Japanese engineers and pilots gathered around the aircraft daily, their notebooks brimming with meticulous measurements, schematics, and observations. The goal had shifted from mere restoration to a complete deconstruction and understanding of the bomber's design philosophy. From the cockpit to the tail gunner station, from the engines to the bomb racks, every detail was scrutinized. Major Kazuyuki Saitito and Lieutenant Shiyama led the disassembly of the first B-17's armament. 13 M2.50 caliber Browning machine guns were removed systematically. Each gun was noted for its robust, reliable construction, crude by Japanese standards, yet astonishingly effective. The engineers observed that American guns were designed to operate under adverse conditions with minimal maintenance. Parts were modular, tolerances generous yet precise enough to ensure functionality. In contrast, Japanese aircraft guns required fine adjustments and highly trained armament specialists. The bomb release mechanisms were next. Saitito and Lieutenant Kurusu carefully dismantled each shackle and actuator. The American system, engineered to be self-adjusting, allowed crews to release bombs rapidly without field calibration. Japanese ordnance, by contrast, demanded meticulous adjustment before every mission. The engineers realized that this design not only simplified operations, but also minimized the risk of human error during combat, a subtle yet profound tactical advantage. September 10, 1943. Cockpit analysis. Test pilots Major Uno and Captain Yagi guided engineers through every control, instrument, and switch. They noted the simplicity and logical layout, designed for efficiency despite the bomber's enormous size. American engineers had reduced pilot workload through systems integration, standardizing controls so that even minimally trained personnel could operate critical functions reliably. April through August 1943 saw continued analysis. Engineers dismantled bomb racks, hydraulic lines, and electrical systems for comprehensive documentation. Every discovery reinforced the reality. American industrial power stemmed from organization, standardization, and precision tooling, not solely from the skill of individual craftsmen. Japanese production, relying on hand-fitting and artisan labor, could not hope to match this scale. Photographic documentation accompanied every stage of analysis. Detailed diagrams of the B-17's hydraulic actuators, cockpit layouts, and engine assemblies were compiled into reports intended for top Japanese aircraft engineers and military planners. Toro Saito, the Asahi Press aviation editor, noted in his March 1943 dispatch that the uniformity and precision of these bombers challenge our most optimistic assumptions about Japanese production capacity. By the end of Part 3, it was clear to Major Saitito and his team that the B-17 represented more than a single aircraft. It was a blueprint for industrial warfare. Its construction revealed a philosophy where tools, machines, and standardized components replaced the need for highly skilled labor, enabling production at a scale Japan could not achieve. The engineers' reports became chillingly candid. In a prolonged industrial conflict, Japan was at a systemic disadvantage. And yet, the B-17's lessons were far from complete. In Part 4, we will explore the detailed analysis of the bomber's armament, defensive systems, and cockpit ergonomics, revealing why even Japan's best-trained pilots struggled to conceive how such a machine could be both robust and easily maintained. These insights would shape not only wartime understanding, but also Japan's post-war industrial renaissance. September 2, 1943. Tachikawa Airfield, Tokyo. The restored B-17ES now dominated the tarmac, gleaming under the late summer sun. The engineers now had 3 operational examples for detailed evaluation and testing. Over the following months, Major Saitito's team conducted exhaustive measurements of airframe structures, wing ribs, fuselage panels, control surfaces, and landing gear assemblies. Each rivet, joint, and stamped panel revealed the depth of American precision manufacturing. Wing spars were machined on automated equipment, panels stamped from master dies, and rivets installed to tolerances impossible to achieve by hand. The examination of the engines provided even more startling insights. Every component, from pistons and cylinder barrels to crankshafts and connecting rods, was uniform across multiple engines. Shimomura noted that American mechanics could swap major components in the field without adjustments, a level of interchangeability Japanese engineers had never achieved. Field maintenance in Japanese aircraft required not just skill, but a lifetime of training. The contrast was undeniable. American mass production reduced reliance on specialized labor while allowing rapid scaling of aircraft output. Test flights over Japan further impressed the engineers. Major Uno piloted maneuvers while Captain Yagi documented gun operation and flight responses. The defensive armament of 13 M2.50 caliber Browning machine guns proved highly effective, providing overlapping fields of fire that created near-impenetrable zones around the bomber. Japanese fighter pilots assigned to practice intercepts realized that even multiple coordinated attacks often failed to disable the aircraft, highlighting the tactical advantage of both the design and production philosophy. May 15, 1943. The first leg of the flight commenced. The B-17s, escorted by Ki-43 Oscar fighters, lifted into the humid morning air. Pilots Major Uno and Captain Yagi, with engineers observing from the rear seats, recorded performance data and system responses. Every vibration, control input, and engine parameter was noted. The Japanese airmen, accustomed to aircraft requiring constant manual adjustments, were struck by the B-17's remarkable stability and ease of operation. Systems that would have required specialized attention in a Japanese plane functioned flawlessly with minimal intervention. During stops at strategic airfields along the Malay Peninsula, the Japanese engineers continued their examinations. In one instance, at an auxiliary airstrip near Malacca, engineers disassembled the bomb release mechanism and hydraulic actuators, cross-referencing the results with manuals captured from American crews. Lieutenant Shiyama remarked on the precision tolerances, noting that the mechanism could withstand repeated deployment without adjustment, a stark contrast to Japanese ordnance systems that demanded constant calibration by armament specialists. The journey over the South China Sea presented additional challenges. Tropical storms forced the formation to alter course, and engine monitoring became critical. The B-17's R-1820 Cyclones proved their reliability, operating efficiently under high humidity and heavy rainfall. Engineers observed that even in adverse conditions, the systems maintained performance, further highlighting the robustness designed into the aircraft. Any misstep in Japanese aircraft could lead to mechanical failure, but here, the B-17 demonstrated the superiority of systematic production combined with durable design. By June 3, 1943, the 2 restored B-17Es safely arrived at Tachikawa Airfield near Tokyo, joining a third B-17D previously captured in the Philippines. And yet, the story was far from over. In the next part, we will delve into the transportation of the restored B-17Es to Japan, the intricate logistics of moving them across occupied territories, and the first flights over Tachikawa Airfield, a chapter that would solidify the engineers' understanding of American industrial supremacy. May 8, 1943. Singapore and the Malayan Peninsula. The restored B-17Es, carefully reassembled by Japanese engineers at Malong and Mayon airfields, were ready for their perilous journey to Japan. This was no ordinary flight. It was an unprecedented operation requiring meticulous planning, coordination, and secrecy. Escort fighters and transport aircraft were assigned to protect the bombers from misidentification and potential engagement by Japanese air defense units along the route. Nakajima L-2D transports, license-built versions of the Douglas DC-3, acted as motherships, carrying spare parts, fuel, and technicians. Every air defense unit along the path, from Singapore to the Japanese mainland, received precise flight plans to prevent friendly fire incidents. The engineers overseeing this operation were acutely aware of the stakes. Major Kazuyuki Saitito and Lieutenant Kurusu meticulously documented every step, ensuring that each component of the B-17s remained intact and operational. The restored Wright R-1820 Cyclone engines were checked multiple times, hydraulic systems pressure tested, and electrical circuits verified for continuity. Even minor discrepancies could prove catastrophic over thousands of miles of open ocean and jungle terrain. Meanwhile, detailed measurements of wing spars, ailerons, and elevators revealed the B-17's reliance on automated tooling. Wing ribs were produced with hydraulic presses, control surfaces formed from master dies, and rivets installed with semi-automated machinery. Testing damaged components revealed tolerances that would have been impossible to achieve manually. Rivets varied by less than 0.0001 inches in depth, installation precision that Japanese factories, relying on skilled hand riveting, could not approach. Japanese publications began documenting these findings. Aviation editor Toro Saito from Asahi Press toured the airfields and counted at least 4 B-17Es ready for evaluation. His reports highlighted the extraordinary degree of mass production and standardization, emphasizing that these aircraft could be maintained and repaired by mechanics with basic training, a concept that contrasted sharply with Japan's reliance on skilled labor. April 20th, 1942, saw the first comprehensive team meeting at Malang Airfield. Saitito addressed the gathered engineers. The B-17 is not merely a plane. It is a product of an industrial system designed to outpace any single nation's ability to compete. Every component is made to fit, every system designed for rapid maintenance, and every assembly line capable of producing replacements faster than our factories can build fighters. We are observing not just machines, but a philosophy of warfare embedded in production itself. By the end of Part 2, the Japanese engineers had cataloged the B-17's key systems in exhaustive detail. Engines, hydraulics, electrical wiring, bomb release mechanisms, and defensive armament were all studied to uncover American secrets. The sobering realization had begun to take root. Japan's reliance on artisan labor and hand-fitted components made it impossible to match American industrial output, and this captured bomber was proof of that stark reality. Wiring harnesses employed machine crimp terminals, consistent wire gauges, and modular circuit breakers that could be swapped with minimal training. Japanese aircraft, by contrast, relied on hand-soldered connections and individualized circuitry, requiring specialized electricians for repairs. Even the B-17's oxygen delivery system demonstrated precision engineering, with regulators bearing manufacturer stamps from automobile part suppliers, a testament to the adaptability and scale of American industry. By mid-March, engineers began reassembling parts from multiple damaged aircraft to create functioning B-17Es. This required captured Allied mechanics and Japanese ingenuity, combining salvage components to restore two bombers to airworthy condition. The process was painstaking, often taking weeks for each subsystem. Engine assemblies were calibrated, hydraulic lines pressure tested, and electrical systems rewired according to the translated American manuals. The work demanded patience and a deep understanding of the bomber's design philosophy. April 10th, 1942, marked a significant milestone. The first restored B-17E lifted off from Java's Malang airfield under the watchful eyes of Japanese engineers and pilots. Test flights revealed the bomber's handling, fuel efficiency, and defensive capabilities. Major Uno and Captain Yagi, flying alongside in key 43 fighters, recorded every maneuver, gun operation, and structural response. Despite flying outdated Japanese interceptors, they quickly realized that a single B-17 could withstand multiple attacks, its armor and defensive guns creating a deadly envelope of protection. The implications were stark. The Japanese engineers now understood that even if their pilots could shoot down one or two bombers, American factories could replace them far faster than Japan could produce interceptors. The war of attrition, the engineers noted, was already skewed heavily in America's favor. The team, still led by Major Kazuyuki Saito, divided their efforts across structural analysis, engine evaluation, and subsystem documentation. Lieutenant Kurusu focused on the airframe, measuring every rivet, spar, and fuselage panel. Lieutenant Shiyama and O'Hara concentrated on the propulsion system, dismantling the Wright R-1820 Cyclone engines and cataloging every component down to nuts and bolts. Shimamura meticulously studied the hydraulic lines, bomb release mechanisms, and fuel systems, while test pilots Uno and Yagi prepared for initial flight assessments. The more the engineers examined, the clearer the contrast became. The fuselage, wing spars, and control surfaces revealed precision stamping and die forming. Panel thickness was consistent across multiple aircraft. Rivet holes aligned perfectly between different B-17Es, demonstrating a level of standardization that Japanese factories could not replicate. In comparison, Japanese aircraft production relied heavily on artisans who individually fitted parts, often requiring adjustments for each aircraft. Every replacement part was a custom fit, demanding skilled labor, a bottleneck American industry had bypassed entirely. Attention quickly turned to the engines. The R-1820 Cyclone's assembly astonished the engineers. Pistons, cylinders, connecting rods, and crankshafts were machined to tolerances measured in thousandths of an inch, perfectly identical across engines. Shimamura noted that any cylinder from one engine would fit seamlessly into another without adjustment. The hydraulic system exhibited similar ingenuity. Standardized fittings and couplings allowed rapid field replacement of actuators, lines, and valves. Every subsystem, from the fuel pumps to the bomb release mechanisms, prioritized modularity and serviceability. In addition to mechanical ingenuity, the electrical systems revealed another level of American sophistication. Despite these insights, Japan continued to study the bombers rigorously. Test flights allowed pilots to experience firsthand the B-17's flight characteristics, defensive capabilities, and operational procedures. Japanese military training films even depicted mock intercepts against the captured bombers. Yet these films never conveyed the full danger. For every B-17 shot down, American factories could replace them faster than Japan could produce fighters. By the end of Part 1, the engineers' reports concluded with an undeniable fact. The B-17 was more than a machine. It was a manifestation of industrial philosophy. Its superiority did not lie in engines or aerodynamics alone, but in the systematic organization of production, which allowed America to build overwhelming numbers of combat-ready aircraft with a fraction of the skilled labor Japan required. And yet, this was only the beginning. In the next part, we will explore how Japanese engineers dissected the B-17's engines, hydraulic systems, and electrical networks, revealing secrets of mass production that would influence post-war industry, and why this realization left them with a stark, unavoidable conclusion. March 5, 1942. Malang Airfield, Java. The morning air was thick with humidity, carrying the faint scent of diesel, oil, and wet earth. Here, Japanese engineers began the meticulous task of examining additional B-17Es scattered across the captured Dutch East Indies airfields. Among these aircraft, one in particular drew immediate attention. B-17E serial number 41 to 2459, damaged in its crash landing but remarkably intact. The engineers approached it with a mix of curiosity and caution. Each panel they inspected, each engine they partially disassembled, reinforced a growing realization. American industrial methods were unlike anything Japan had seen. By late March 1942, the engineers had documented multiple B-17s scattered across Java, with at least 4 examples in varying conditions. They began the painstaking process of restoring 2 bombers to flight-ready condition, using salvage parts and captured Allied mechanics pressed into service. The work involved understanding unfamiliar systems, translating American manuals, and reconstructing engines, electrical networks, and hydraulics. Months of meticulous labor culminated in the B-17s being prepared for their journey to Japan, a flight requiring careful coordination to prevent friendly fire incidents across Japanese-occupied territories, escorted by Nakajima L-2D transports and fighter units. By mid-1943, the bombers arrived safely at Tachikawa Airfield near Tokyo, joining a B-17D captured earlier in the Philippines. Now, Japanese engineers had 3 examples for detailed evaluation. Every structural member, every mechanical system, and every subsystem was measured, disassembled, and cataloged. Wing panels were stamped from massive hydraulic presses, rivet patterns analyzed, and control surfaces compared for uniformity. Engines were studied down to individual piston rings, cylinders, and bearings. The engineers quickly realized the sobering truth. The United States had achieved a level of industrial standardization and mass production Japan had never approached. Observations were compiled into detailed reports, highlighting the contrast between American and Japanese manufacturing philosophies. American production emphasized interchangeability, ease of maintenance, and rapid scalability. Japanese production relied on skilled labor, handcraft adjustments, and intricate field maintenance. For Major Saitito and his team, the implication was stark. In a sustained industrial conflict, Japan could never match the pace and scale of American output. Attention quickly turned to the engines. The B-17ES Wright are 1820 Cyclone radial engines, once disassembled, revealed hundreds of parts machined to tolerances measured in thousandths of an inch. Crankshafts, connecting rods, pistons, cylinders, all perfectly identical across engines. Major Saitito noted that field mechanics could replace entire engine components without the need for skilled adjustments, a system that relied on manufacturing precision rather than human craftsmanship. In comparison, Japanese aircraft engines demanded highly trained technicians, and maintenance often involved hand-fitting parts. The hydraulic and electrical systems offered further evidence of American ingenuity. Hydraulic lines used standardized couplings, actuators and valves were modular, and the entire system could be serviced quickly with minimal training. Electrical wiring employed machine-crimped terminals, uniform wire gauges, and modular circuit breakers, allowing rapid replacement in the field. Japanese aircraft, by contrast, relied on soldering, adjustable contacts, and skilled electricians for maintenance. The cockpit itself exemplified the B-17's design philosophy. Controls were simplified, integrated, and intuitive. The oxygen system featured precision regulators stamped with manufacturer marks, often made by automobile part suppliers, companies that had no prior aircraft experience. Even the defensive armament, 13M 2.50 caliber Browning machine guns, combined simplicity with effectiveness, creating overlapping fields of fire that were easy to maintain but deadly in combat. Japanese fighter pilots participating in practice intercepts were quickly impressed and alarmed by the defensive coverage and durability of the bomber. February 12, 1942. Mayoan Airfield, Java. The morning mist clung to the grass and puddles of the captured airfield, where a Boeing B-17E Flying Fortress, serial number 41 to 2471, sat silently among the wreckage of hastily abandoned American aircraft. Its engines were missing, the nose section torn apart from a rough landing. Yet the bomber's structure remained largely intact. For the Japanese soldiers patrolling the area, it was just another trophy of war. But for the engineers dispatched from Tokyo, specialists from the Koku Jujutsu Kenkyujo, Japan's pinnacle of aeronautical research, it was the key to a revelation that would challenge every assumption they held about industrial capability. Within days of the airfield's capture, a team of Japanese engineers arrived, led by Major Kazuyuki Saitito, an aeronautical expert with years of experience in aircraft testing and design. Alongside him were Lieutenant Shiyama, Lieutenant Kurusu O'Hara, Army Assistant Engineer Shimamura, test pilots Major Uno and Captain Yagi, and propulsion specialist Kaneo. Their mission was clear: document every component of the B-17, understand its construction, and evaluate what made this American heavy bomber so formidable. At first glance, the airframe seemed ordinary. Aluminum panels riveted together, wings spanning over 100 feet, and fuselage sections that were strong yet surprisingly light. But as the engineers measured rivet spacing and inspected the structural members, a profound pattern emerged. Every part was uniform, standardized, and precisely manufactured. Rivets aligned perfectly across different aircraft. Wing spars, ribs, and panel sections were interchangeable, a level of consistency that Japanese aircraft, crafted by skilled artisans, could not match. Japanese planes often required field modifications to fit replacement parts, whereas the B-17's components could be swapped without adjustment. February 12, 1942. Jaffa, Indonesia. The sun rose over a muddy, rain-soaked airfield, revealing a sight that would haunt Japanese engineers for years to come. There, lying in silent defiance, was a Boeing B-17 Flying Fortress, serial number 41 to 2471, captured almost intact after its American crew abandoned it in haste. To the Japanese soldiers, it was just another piece of enemy hardware. But to the engineers from Tachikawa and the Koku Jujutsu Kenkyujo, it was a revelation, an artifact that exposed a level of industrial sophistication they had never seen before. As the engineers inspected the bomber, every rivet, panel, and component told a story of precision and mass production far beyond Japan's capabilities. Engines disassembled to their cores revealed perfectly machined parts, standardized to the thousandth of an inch. Electrical wiring, hydraulic systems, and even bomb release mechanisms demonstrated a philosophy that merged simplicity with reliability. Machines designed to be maintained, repaired, and reproduced rapidly, without the need for highly skilled artisans. Every observation struck a deep chord. Japan had relied on craftsmen, meticulous hand assembly, and specialized maintenance. The B-17, however, operated on a system where tools and automation did the work once reserved for human hands. It was a silent indictment of Japan's industrial approach and a warning about what lay ahead if they could not match it. Before we dive into the full story of how these capture bombers reshaped Japanese engineering forever, hit that subscribe button and turn on notifications, because in the next segments, we'll uncover every secret they discovered, every technical marvel, and the sobering conclusions that changed the course of aviation history. Trust me, you won't want to miss a single detail.